I'm very proud to be here in the first seminars of this new courses. This is just an introduction to these two fields. It is just one field with a lot of subfields, artificial intelligence and cognitive science. And I want to show you how these disciplines are connected to some philosophical, very present-day issues, but also with some technical issues. So, this is my outline. I will speak about artificial intelligence. AI usually is the why I will call it, and then I want to speak about what it is. I'll start from the beginning, from the disciplines that concurred to the birth of artificial intelligence, and then I will deal with just some of the developments a lot of through the last 70 years, and I want to connect these first topics with cognitive science. So why cognitive science is so important for artificial intelligence and vice versa. And then I want to show you briefly some modern approaches to these two disciplines. So this is a very well-known picture in cognitive science. It's the cognitive hexagon. It's a scheme of the 6 traditional disciplines that are considered at the basis of cognitive science: philosophy, psychology, linguistics, computer science, and artificial intelligence, or computer science that is connected to artificial intelligence, and neuroscience. And anthropology. Anthropology is the lowest one, because for some historical reason that I won't go through. But you can see also the connection between these disciplines, among these disciplines, to have this also all these subfields like cybernetics, computational linguistics, neuropsychology. You can see the connection. For example, number 4 is simulation of cognitive processes. It's between psychology and computer science. This is one of the main topics of cognitive science between the 50s of the last century and the 70s or 80s. And also we have the connection between neuroscience and philosophy, neuroscience and computer science. Neuroscience is disciplines that more recently became a very big part of this field of study. So all these disciplines show that cognitive science is an interdisciplinary field par excellence, and that it is not a simple field, because if you have many disciplines, you have to put them together. You have to put them together. You have to put together the methods, the results, the languages, but cognitive science is tightly interwoven with artificial intelligence, and in some way, artificial intelligence is a field that have the same extension as cognitive science. So someone sees artificial intelligence as cognitive science. Other people, other researchers see artificial intelligence as a technical disciplines, and we will see what is the difference between them, and vice versa. Cognitive science is also seen as a very big part of, or as the same as artificial intelligence. Now, in the mid-20th century, we have the birth of artificial intelligence. Officially, the year of birth is the 1956. But before, we have a lot of transformation in different disciplines, from logic and the birth of mathematical logic in the 19th century. We have many logical results that led to the birth of computer science and computers. And from study on physiology, we have the development of cybernetics. Cybernetics is disciplines that in the 30s and the 40s of the last century studied the communication and control in organisms to reproduce them in artificial artifacts. For example, in war artifacts like missile or airplane. And we will see how this is important for artificial intelligence, for the birth of artificial intelligence. So logic and physiology and also mathematics and psychology are at the basis of the birth of artificial intelligence, but also linguistics. But before see linguistics, we have to speak about Alan Turing, that is considered one of the father of artificial intelligence for two reasons. The first one, Alan Turing died in 1954, and 1 or 2 years before the official birth of artificial intelligence. So he never spoke about artificial intelligence, but he is the father of calculation in computer science and the father of the idea to have the idea of thinking machines. The first achievement of Alan Turing is in the 1936, is the Turing machine. The Turing machine is not a concrete machine, it's an abstract machine that is a model of computation. So it's an abstract model of computation. What is a Turing machine? It's a set of instructions. Every Turing machine is a set of instructions that are used to go from an initial state to an ending state. The initial state is the problem, and the ending state is the solution. This is an abstract machine because this is a formalism that is applied to a mathematical problem. But this is also a logical device, because in its formalistic way, use very, very simple instruction to define what is what we can calculate in an automatic way. So in a Turing machine computes anything that is computable. What is computable? A process is computable if we can go from an initial state to an ending state, and there is a point of where the computation ends. Because there are problems that are not computable, so we cannot have a solution. This is a logical or mathematical problem. But what is the translation in a practical way? If we have a problem that does not finish, it is equivalent to a program that does not work, because every program is a sequence of steps that are ruled by instructions. So a Turing machine is nothing but a program. Now, the formalism is based on an infinite type with infinite cell and a head, a state register, and a set of instructions that define rules or moves of the head along the tape. In this way, Turing defined computation as physical transformation on this tape without ambiguity. Why without ambiguity? Because it is a logical process. No? In logic, we don't have ambiguity. We have a sequence of steps that a machine, a calculator, a computer can bring together to an end state. So this is the idea of Turing. We have the tape, we have the head that is able to can write or read a symbol on the tape, and this is the state register where the instructions are present. This is an elaboration typical of a Turing machine. This is, I think, running on an addition or something like arithmetic operation. You see, the point is that the instruction that define a Turing machine are very simple instruction, and Turing machine makes very simple operation. And this is the basis of what a computer do at the level of machine language. Now, why is this so important for artificial intelligence and cognitive science? With the definition of a Turing machine, Turing is able to define what is decidable, so what is computable in a finite number of steps. So which problems have a solution. And the definite method of Turing machine, that is a program, is a sort of algorithm. Is an algorithm in the very sense. The other important part are the symbols that can be written or deleted on the tape. And the state of the machine is equivalent to a state of mind. Why we can see this equivalence? Because in an interpretation of this abstract model of computation, the calculator is, for Turing, according to Turing, is equivalent to a human being that calculates something in an automatic manner. So we can see the fact that we operate with symbols as the same as a calculator that operates with symbol. This equivalence is at the basis of cognitive science, at the very first metaphor of cognitive sciences and artificial intelligence, that the mind is a computer. We will see other metaphors, other analogies in the other slide. And what is undecidable is not computable. So what is mathematical, logical, undecidable is not computable. There is no program that could compute this kind of problem. But what is important is that if you can translate your mental processes in something that is definable with symbol, you can also replicate that on a machine or a universal Turing machine. Why universal Turing machine? Because the Turing machine is a single problem. The universal Turing machine that universalizes the procedure is a machine that is able to have the instruction and the data. So this is the very equivalent to the modern computers, where we put inside the program and the data, and we have the solution, the results of the procedure. So data instruction are both on the tape. So it is equivalent, it is tantamount to say that they are expressed by symbols, by the same symbol that in the computer are O and 1. So the universal Turing machine is the modern digital computer. So now, so far we have a Turing machine that is an equivalent to a procedure, to a program that is able to execute something, and the idea that the state, the internal state of the machine are equivalent or could be equivalent to the internal state of the mind that operate on symbols. Now, okay, the modern digital computer like this one, the same. Okay. Now, Turing was a very open researcher, open-minded researcher, and he dealt also with the brain. Why? Because the brain is the organs in which the mind is implemented. And he tried to study also the brain and to produce something about intelligence starting from the brain. In 1947, 1948, he wrote some papers on this topic. Why? Because he saw the brain as the perfect learning machine, and learning is at the basis of intelligence. Why the brain is the perfect learning machine? Because the brain is an initially unorganized networks that in the development during the years became an organized network, so an organized machine able to learn. And so the last question by Turing is, can machines think? This is a question in a very well-known paper of 1950 on computing machinery and intelligence. Can a machine think is the most philosophical question by Turing, and he tried to deal with these questions in this way. He says that the question about thinking machine is too vague and too stupid, and we have to consider special machines that are digital computer, and we have to see if in a game that he called imitation game, a human being is able to recognize if he is in a linguistic conversation with a computer or with a human being. This is the very well-known Turing test. The Turing test also in this day there are contexts about Turing test, about programs that are able to pass for human being to pass the test, and the original idea is what if I am in a linguistic conversation with something or someone that is answering to my question. Why the question-answer form for this test? Because the language, and this is the first affirmation, the first strong claim on language, the language defines intelligence in these years, in the mid of 20th century, and in a domain in which machines and human beings are not to be compared for their body. So symbols, language, intelligence are at the very core of the birth of artificial intelligence in the mid-20th. So it's a little comics. The question is, can a computer talk like a human? And this is also a question that is very relevant. Why? It is not just a joke, because if you can have an interaction, a linguistic interaction with a computer, as in many things today, like in the vocal assistant, or when we have we have to do something related to some text, some corpus of writings. The problem is the same. Is it possible to treat the language in a human-like manner, conversational, or just treatment of information? Many information today are expressed by natural language in a digital way. That is also the topic of this these new courses. The other part is cybernetics. Cybernetics, I said, is the science of that studies the or studied in the 30s and 40s and 50s the control and communication of information inside the organism to reproduce them in artificial artifacts. So cybernetics studies self-regulating systems and circular causality, so systems in which there is no a linear causality, but what is important is to maintain an harmony or a state of equilibrium, and systems that in which the random behavior evolve to an organized behavior. How? Through feedbacks from the environment in which the systems is embedded. So the most famous example is the missile that has to catch an airplane. The airplane is driven by a human, a pilot is a human being, and the missile has an artifact, an artificial artifact that reduce the distance, changing its trajectory to catch the airplane. This is the work of Norbert Wiener, that is the father of cybernetics. But what is important here is not a war success or an army success. The important is that in those years when mental and psychological issues was not considered something of scientifical, because of psychology was behavioristic. Behaviorism was the main psychological trend. Something in logic or in mathematical studies as Turing, or in cybernetics as Norbert Wiener, reintroduce a mental or a teleological languages to discuss autonomous systems. And this is at the very base of the birth of the possibility of artificial intelligence. Because we can see artificial intelligence as something that deals with intelligence, or something that deals with autonomous system. And at the beginning of this trend, the stress was on intelligence. Today is on, as we will see, on autonomous system. So these systems are also purpose-oriented. So the teleological language, they have an aim, a goal, a target that has to achieve. Information is what is inside these artifacts or systems, and is what guide the behavior of these systems. Now, I have two different machines to explain what is the difference between a mechanical device and a cybernetic device. This is a typical representation of a mechanical device, a clock with the the mechanism inside. Every single step, every single discrete step is due to the step before, and we have a sort of linear development of the behavior of this machine. This is the Watts governor for steam engine. It's a simple device that is connected to the power that is generated by the steam engine. If we want to put the power at the same level, we have to use this device that open the throttle, the valve, when the throttle valve when the power is lowering, and close the throttle valve when the power of the machine is growing too fast. So it's a simple device of 18th century that explain the idea of feedback, the idea of equilibrium, and that is at the basis of every single system, such as biological and living systems that have to maintain a sort of equilibrium. Okay, in the same years, other people studied the neurons and the possibility to have digital neurons. For example, McCulloch and Pitts in 1943, they study the possibility to reproduce neurons, and so they gave birth to a sort of a computational psychology or computational proto-neuroscience using a sort of simplified abstract neuron, just the threshold, the function of threshold and the connection between them. And, but this is just a model of a real thing, a model of something that they reproduce with this kind of schemes. And why this is important? Because neurons, our brain is at the basis of our mental, psychological, cognitive process. Besides, and finally, we have this engineer, Johann von Neumann, mathematical and mathematician and engineer, that provides the scheme of the computer, of every computer, with input and output devices that you know very well, and the units that are necessary requirement for computation or calculation. A memory unit, random access memory, and a central processing unit, that is a unit of control, and an arithmetical logic unit. This is the translation, the technical translation of a universal Turing machine. Now, this is a quotation from a proposal that gave birth to the artificial intelligence. We propose that a 2 months, 10-man study of artificial intelligence, the first time that this expression is used, be carried out during the summer of 1956 at Dartmouth College in Hanover, in New Hampshire. This study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. This is the key word. An attempt will be made to find out to make machines use language, form abstraction or concepts, solve kinds of problems now reserved for humans, so for human intelligence, and improve themselves. We think that improve themselves so are self-regulating and self-changing machine. We think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer. Very, very optimistic. This is you can find the whole text of this proposal for a seminar, with also all the numerical and money details that they required for this project. Why we? Who is this we? We are 4 people, John McCarthy, Marvin Minkey, Rochester and Shannon. As you can see, there are no philosophers or psychologists. We have a logician, mathematical logician, other people that work as engineers or in something technical fields. So artificial intelligence is was not thought as a discipline for study psychological state of psychological function, but soon became also this one. So we have 2 perspectives on artificial intelligence. The first one is the psychological artificial intelligence, the idea that simulating that kind of cognitive function is a sort of understanding of intelligence and cognition. So simulating that function, abstraction, concept, categorization, language, and so on, is a good explanation of this kind of phenomena. And the other one, the engineering AI, the idea that we can reproduce the intelligence, does not matter in which way, because from this point of view, we are not interested in cognition. And we will see if it is possible or not. But these 2 perspectives were interwoven in the first decades of artificial intelligence. Intelligence, as you can see, is the common topic, but this is a sort of explanation way of consider the use of simulation on computers with programs, and this is a practical way to consider intelligence. Intelligence is what human beings do, and artificial intelligence is to reproduce what human beings do outside, in their behavior, not in their mind. Okay, this is the question. Is it possible or useful to avoid cognition? Can we avoid cognition? Can we have an engineering without considering the cognition? I hope that at the end of this presentation you will see that the answer is partially no. Alan Newell and Herbert Simon are other 2 fathers of artificial intelligence, especially of psychological artificial intelligence. They are not psychologists. Herbert Simon is worked in economy. Alan Newell was a physicist, and Herbert Simon works in economy. He studied administrative organization and how it influences decision-making processes, and he found that human beings use heuristics, so sort of rules of thumb to solve their problem, that they have purposes, they have target, they have goal, and that the goal defines a way to solve a problem, and that the best or the more common heuristics is the means and analysis, so the analysis of what we have and what we have to achieve. Why these are so important? Because if you want to replicate the human intelligence, you have to consider that the human beings have a sort of bounded rationality, not a perfect rationality. The perfect rationality is the rationality of the perfect agent in a situation. So the agent that is able to choose the right in every situation to do the right choice. But human beings are in a situation in which has limited knowledge, limited information, and they have to refine in the process the knowledge and the information to achieve a solution. So the idea is that the very reproduction of the human being intelligent behavior is to build programs that are able to arrive to satisfactory solution, not optimized one, not optimal solution. Why? Because a satisfactory solution costs less than a perfect solution in many ways. We don't do in every occasion the right choice, because we have not the cognitive capabilities to evaluate everything. So an intelligent program that is a simulation of human intelligence has to consider this aspect. Alan Newell was a physicist and a mathematician, and he studied with George Polya. George Polya was a researcher that studied the methods of and the heuristics of proof in mathematical proof, and he he asked to the mathematician in which ways they can achieve the demonstration of the proof of a theorem. And he found some heuristics, some strategies. Heuristic is the same as strategy in a simple, to put it in a simple way. He worked at rand comparison, and in 1954 they decided to study the human problem-solving behavior by simulating it on a computer. What is the conception of mind that all these people have and that concur to create the cognitive science? They have a new conception of mind, respect then the conception of behaviorism. That is the idea that the mind is a symbol manipulating system as a Turing machine, and that is also an information processing system. So the idea that the mental, the psychological, is a sort of running to process information. This is also the very birth of the information processing psychology. So the idea that our psychological function are information processing. The method used by Newell and Simon was the protocol analysis. They asked to the problem solver how they achieve a solution. They try to generalize this method and to create programs that use these general methods. So it's a sort of going inside the mind and try to reconstruct the process. In this perspective, artificial intelligence and psychology are strictly aligned in a way and the other way around, because they started to work together. The logic theorist and the general problem solver are the most famous programs of the beginning of artificial intelligence that are in this psychological or cognitive way to consider simulation on computer. These problems have heuristics, so have a construction, a programming of strategies in their inside. They are constructed to solve problems like theorem proof, especially logic theorists. They have goals and sub-goals. They proceed with a process of reduction What is, in which sense reduction? This is the reduction of the difference between the target state and the initial state or the current state. So if I reduce this difference, I arrive to a solution. The space of state are the space of possible state of the problem in which the program is able to find a pathway to the solution. And another interesting thing is that the failure is possible. Why? Because the solution, the best solution in this case is the satisfactory solution, not the optimal solution. So the problem, as human beings do, is able to fail, but is also able to find a solution in that cost much less than the optimal solution. The thinking aloud by subjects is the method of protocol analysis. It's the method that is used by Alan Newell and Herbert Simon to find out what are the strategies of the experts in their fields. So, what is the target, the goal of these two researchers? The program has to work. No, it is very trivial. But the program has to work in a human-like manner, because if it if it runs in this way and it works, means that the program has to arrive to a solution, a satisfactory solution. You can consider this working as an explanation of a psychological theory. So, at the end of the running, there was a comparison between the human account and the program trace to see if there is a better solution, a better way to solve it, but if this could be considered an explanation of some psychological theory. We can consider this one a sort of introspection. Introspection is a very hard topic for psychology, because psychology knows that introspection is not a useful method because it's too subjective, but it was used to build the first program, and it became, for some developments in artificial intelligence, for example, in expert systems, a useful and a traditional way to build programs. In this perspective, the AI programs were used for, are also used today for modeling, criticizing, and improving psychological theory, and to simulate a sort of non-numerically thinking. Someone in philosophy started to consider this kind of using computer science a sort of a solution of mind-body problem. And just for the sake of discussion, in philosophy of mind, this very first moves on artificial intelligence led to functionalism. So the idea that the mental state are the state that they assume in a discrete process of a finite number of steps. So every thought is cause of other thoughts that are consequentially. The last father of cognitive science and not artificial intelligence, but computational linguistics, that is very strictly related to artificial intelligence, is Noam Chomsky. He is still alive. And he wrote in the 1956 a book, very well-known book that is, the title is Syntactic Structures. And he applied some new idea about the mind and the cognition, about the existence of something in the mind to the language. He gave birth to computation related to language and to psycholinguistics, or computational psycholinguistics. The three issues, or three aspects of his main ideas, that the syntax of languages could be formally described as a generative systems, that the sentences of a language has more levels of representation, and that we can define the grammatical transformation to have a formal system that is able to catch the power of the syntax of language. This is a tree diagram of the superficial. We saw that we have more levels of representation. This is the superficial structure. It is the sentence, the cat slept on the carpet. This is the deep structure. Where is this deep structure for Chomsky? This deep structure is inside the mind. The mind as a device that is able to produce or understand every correct, syntactically correct sentences of a language. Okay, we can use, or Chomsky used this theory to catch the formal power of syntax. He said that every language could be described as a grammar based on rewriting rules. This is also just an example. Sentence is composed by noun and verb. Verb are auxiliary plus verb. That is the articles or something like that. And with these rewriting rules, we can construct the sentence. So from S, that is a sentence, the instantiation is by rule 1, 2, 3, also the same rule applied more times. We can arrive to the man will hit the ball in a baseball contest. So why is important? This is important for two reasons. Because if we can formalize the rules at the basis of language, we can construct formal system that automatically treat the language. Today, these formal systems are parsing systems, so parsing programs that are able to analyze and treat automatically the syntax of a language. And the other reason of the importance of Chomsky was that, of the Chomsky theory, that the language acquisition device was the first device, the first module that was considered inside the mind that produced mental states, like the head and the state register of the Turing machine is able to understand and to build sentences of the natural language that is spoken by someone. And this is the new course of psychology. The idea that in mind we have something, what we have inside the mind. We have modules that are dedicated to different cognitive processing, language, recognition, mathematical operation, memory, and so on. And so the idea that was developed by Jerry Fodor, that was also a philosopher but also a student of Chomsky, is that the mind is modular, the modularity of mind. So we can explain our cognitive function considering what is in our mind like a system like this. with subsystems and so on. The interesting idea is that we are not in a Cartesian world. We are not able to see inside us everything of this. In cognitive science, the 90% of the mental operation are not conscious. No, there is something in the mind, but there is also something that is not conscious. So the mind in cognitive science and in artificial intelligence becomes something that has representations of external world and procedures. And this is the computational representational theory of mind by Jerry Fodor. But what kind of representation? We can ask what is the type of our mental content, how are our concepts? We will see soon. Before, we have to see what is a model. A model is something that, if it works, is quite similar to a program. No? We can have a model is a kind of program that runs when have some input and gives some output, because is biologically evolved but is encapsulated. So like a routine that start to operate when have the right input, give some output that go to other outputs that go to other models. So when we have in this conception of mind, when we have some perception of our outside, the model of perception elaborate this information, and then the outputs go to other models and so on. The computation is automatic. You cannot do anything but understand what I'm saying. You cannot avoid to understand what I'm saying. You cannot listen to me. But if you listen to me, you understand that at least syntactically my sentences are right, and you understand the things. Every model is domain specific. This is the model for language, for perception, for memory, and so on. And these are also import cognitive capabilities. In this theory, with Chomsky and his legacy, the concept of inborn became central again after a period in which this was considered just a philosophical and not useful conception. This is just a little illusion to see how we can consider a model encapsulated and automatic. I can say you and show you that these two lines are equal, but the illusion is that even if you know that these two lines are equal, you cannot doing anything but perceiving them as different, because the perceptual model see that they are different even though they are similar because of these little lines. Another one, more famous Kanit's illusion, there is no a triangle, but you perceive a triangle inside. This is just an exemplification of what is this idea that we have subroutines in, or the mind is composed by different subroutines. So, in this new way of cognitive science that is supported by artificial intelligence, the mind, the first analogy, the analogy with the capital letter, is that the mind is mental representation plus computational procedures, and this is equivalent to thinking. The program is data structure that are related to mental representation plus algorithms that are the procedures, and thinking is equivalent to running programs. So the analogy is that the mind is a program. Is the very traditional analogy that is traditional in the traditional or good old-fashioned artificial intelligence, that is the approach between the 50s and the 80s, the symbolic approach. But we can have also other analogy. Mind is a computer, brain is hardware, brain is to software as brain is to hardware. Why all these analogies? Because these are at the basis to the epistemological study of artificial intelligence and cognitive science. Is it true that we can study cognitive function and reproduce it with programs or not? For example, Paul Taggart, another is a contemporary researcher on cognitive modeling, says that we have an analogy between three entities, the computer, the brain, and the mind, or between minds, computers, and brains. And these are three couple that has to be considered in study the mind in an artificial manner. We can refine this cycle in another way. We can say that if we start with a theory about some intelligent behavior or capabilities, we can construct a model, and then we can write a program and implement it on a platform to evaluate if the theory is right. This cycle is useful also if you study the brain, or if you use the simulation of brain, as we will see soon. Now, this is another step in the history of artificial intelligence. In the 70s, this was the case, or the best case as a cognitive function has to be studied. This is the case of the vision by David Marr and Tommaso Poggio. They say that every time you have a cognitive function, you can analyze it in a computational manner that produce something that is algorithmic, and then you can reproduce, implement it on a computer. And this is also consistent with the idea that we have a computational explanation of psychological functions that are implemented on our brain. But this is what the program on vision do. He was able to catch some difference in the light and transform them in pieces of some images. In this case is a human being. So, summing up, what are the typical artificial intelligence features or topics? Problem solving, we saw, and planning, the way we can have a program that will plans. Decision making, how to simulate this very, very general capability of intelligent human being. Learning from outside, that goes from perception to creation or building of new methods. Natural language processing, because language is central in our way to communicate, and most of our knowledge are expressed in natural language, or in also especially in writings, and knowledge representation. So the field, the subfield of artificial intelligence that is dedicated to the way to represent knowledge in an autonomous system in order to have a system that is able to use usefully this, or fruitfully, this knowledge as a human being. And also every psychological and neuroscientific today related issues. Knowledge representation was and is today one of the most important field in artificial intelligence because, and also in cognitive science, because because it's an hard problem for artificial intelligence. Our knowledge is not expressed in a logical form, and usually the way in which we represent knowledge, the way in which express how a domain is built, how the concept in a domain are structured, is the very intelligent part of the problem-solving process, or of a program that is dedicated to solve a sort of problem. So the knowledge representation is absolutely needed for intelligence, and we have to consider, and this is more and more truer and truer today, that the mere information is not knowledge, and that the passage from information to knowledge is another very important part of intelligence. So in the first artificial intelligence systems, and also today, we can use logical methods to represent knowledge. What are the logical methods? Propositional way, the propositional calculus with connectives and propositional variables, and the predicative calculus that uses quantifiers, and you can represent properties and relations among variables, and so object at instantia the variables. And also declarative logics that are useful to express through assertions and facts as what is the situation in a specific domain. Why this is not the best way? This is the best way from a computer science point of view, because programs are and programming languages are logic. We can have different kind of logic. We have to use, especially in artificial intelligence, non-monotonic logic, but this is a problem inside logic. This is not useful to catch the power of cognitive knowledge, because we have representations that of external world that use different ways to categorize the external world. For example, is most likely that the human knowledge is a sort of semantic network where every concept is connected to other concept in a hierarchical or hierarchical way. This a network, a semantic network, catch the power of the conceptual associations that are very, very important in human being knowledge. And we can see that ontologies, computer science ontologies, are a sort of development and complexification of semantic networks. So this is, you can express this in a logical way, but at a more abstract level, this is a way to catch the conceptual association, conceptual structure that define the knowledge of a system. Other systems that was used in the 70s and the 80s are, for example, just one example, the frames that catch the idea that we have a core in our concept with some feature that are more more typical, and other that are specific of the single individuals that we consider. For example, a dog has 4 legs, but we can have also a dog with 3 if he's not so lucky. And this kind of tools were thought to represent also the exceptions. Now, networks and concept. Using the networks was the one of way to catch the prototypically effects of concept. That was a development in cognitive science in the 70s, in the 80s, and the idea that the concepts are prototypes or example collection or theory of something. All these new many theory of concept were built in contrast the classical theory of concepts. So the idea that a concept is a definition of a complete list of traits that an individual has to have to label it with the concept word. This conception is very, the classical conception of concept is very suitable for a logical treatment, but also in this case, the prototypically effect are far from being in a classical way. And this prototypicality effect and this conception, different conception of concept, are used to explain the flexibility of knowledge, a flexibility that it is useful also in artificial systems. So this is the one of the most important example, the idea that we have a prototypically idea of a bird that is far from a penguin, that is also a bird, but if I say you think of a bird, you maybe think of a bird like this, and the other bird are far from the core of the category, and the concept of the categories are something that has a core and a cloud of other features that are less typical. It's a very long study. There is a very huge literature that I cannot go through now, but just to give you the idea that the knowledge representation has had to deal with these kinds of problem. The successful case in artificial intelligence with logical method was the expert system. The expert system are knowledge systems in specific domains, are not general purpose systems, and they are in the technological perspective on artificial intelligence. There is no human-like knowledge because they are a repository of a lot of knowledge on a specific domain in one field of science, one field of medicine, and so on. And they are built from expertise of human expert, asking the methods of to the human expert, maybe some scientist, and they are a repository of a lot of rules that starting from some input that are the condition of a situation or the symptoms of disease, they give a guess on maybe the disease with some degree of probability. So expert systems are a success, but are intelligence not in a human-like way. They are a very well-known example of knowledge engineering because the construction of this repository and the inferential engine that operate inside this, for example, machine Dendral Watson, this is one of the most recent, that is a medical assistant for a specialized student. They help the human expert, so they don't replace the human expert or the human being. They are a support for human expert. They are not so flexible, and they are not general. They are very specific. They are useful, but they are not an explanation of what reasoning is. So the problems in knowledge representation and the limitation of symbolic logical tradition led to the new artificial intelligence and the new cognitive science. This is a consequence of the failure, or some failures of symbolic approach, that is not a general failure. It's just a way to see that in some cases we have to use other approaches. It is also a consequence of a new conception of mind in which a sort of radical reductionism consider what is very important to reproduce intelligence is reproduce the brain. So the brain simulation became, from the 80s and the 90s of the last century, one of the the core topic of artificial intelligence and cognitive science. Neural networks are the best example of this new approach. It is also called connectionism because the connection in these networks are what elaborate. The neuron studies became at the end of the 19th century, but we also saw that McCulloch and Pitts studied the possibility of reproduce logical neuron. And also in the 60s and the 70s, Rosenblatt and other people tried to build machines that were inspired to the functioning of the neurons, or the portion of the brains, like the perceptron. In 1986, Rumerald, McClellan, and colleague, the research group, published the Parallel Distributed Processing, a very technical book on this new approach to computation and to artificial intelligence, but also a technical book, but also with the philosophy. The main idea is that the symbols are not so important to reproduce some intelligent aspect. What is important is to reproduce the behavior of this kind of machine. What kind of a machine is this? The neuron. You know that the neuron has a nucleus and then an axon, and many dendrites that bring in the information, so the electrical information, and the axon bring out the electrical information when the neuron reach a sort of threshold and goes over it. This is a scheme, a structure of the neural network. You can see that the simulation is just an abstraction of neuron. We have the nucleus, the core of the cell, and the connection that represent the axons and dendrites. We have a codification of some inputs in this kind of approach. We have a codification in the input layer, and then on this connection we have transformation that are mathematical operation that influence the electrical input, the passage of information between the layer. All this system is a sub-symbolic system, in the sense that what you can see inside a neural network is just mathematical operations. And so why it is so important? Because many studies shows that if you have a right coding, or you have a coding in a mathematical expression with numbers of something, a face, a sound, a composition of a mineral, then you can train the network to have the right output. With a backtracking procedure, you can run the network for 1,000 running, and you can adjust with this kind of algorithm of backtracking the weight of the connection. Maybe this is more clear. Here is clear, this is the value of the neuron, and the connection have a weight that is the multiplicator of this value. Neural networks are very useful in low-level function, intelligent function like recognition, perception, because they are very robust, and the codification of the input and the decodification of the output is adjusted to arrive in a dynamical way to the best solution. But the point is that this process is distributed on the network, and also the knowledge is distributed. The knowledge of the network is the knowledge of the whole network. You cannot see, as in other programs, a list of propositions that describe the situation in which operate the network, the neural network. We have a lot of different kind of neural network, recurrent, local, in which every neuron is symbolic or distributed. But the point is that the elaboration is not a symbolic elaboration. It is called sub-symbolic computation, that is quite similar, or that is thought as quite similar, the brain computation, so we have no meaning in the networks. But if it is work, where is the problem? The problem is that not all our knowledge is sketched by a network in this way. We can have also the idea that we can train and have learning in this network, and we can see also that the neural network are at the basis of what is today called deep learning, but a lot of symbolic knowledge is hardly treated by neural network. So this tension between symbolic and sub-symbolic is one of the tension between two different approaches in artificial intelligence. The most recent, I'm almost finished, the most recent approaches to artificial intelligence and cognitive science are compressed in this simple expression for e-cognition. That is it's an expression that collects four different new approaches. The first one is the embodied approach, that is the most important. So the idea that cognition and intelligence are not separable or achievable, are not separable from body, or not achievable if you don't consider the sensory motor issues or something that is related to body, And it is not useful to create an intelligence that is separated from body issues. And we will see soon why. The cognition is embedded because we have to consider every system as put inside a situation, inside a context, especially because we want that our autonomous systems could interact with the real world. Even though the real world is just a digital world, just a digital world of the net, but it is a context of other agent or human agent and so on. The other E is enactive. The idea that our cognition is produced by the context, that the object, the situation in which we live, in which an autonomous system behave, is a situation that has some affordances that generate the perceptive and sensory motor, and so the intelligent or autonomous behavior of the system. And finally, the extended, the idea that our mind, our cognition are not just inside our brain, but the cognition is the result of the use of tools as maybe smartphone or computers, or also the language itself, that for Andy Clark, that is one of the main researcher in extended mind field, propose as the best idea, the best tool for extend our mind, language, natural language. Then we can see that the first two are connected to a radical embodied vision of cognition that is connected to some field of artificial intelligence, especially the robotics part of artificial intelligence. Enactive and extended approaches are connected to the extended mind idea, so the idea that not just cognition, but the mind itself is a concept that is to be changed and transformed in collective, distributed ways. Some new approaches and some application of these approaches of artificial intelligence and cognitive science, just to see what I was saying you in the beginning, that the technological, engineering, and psychological or cognitive artificial intelligence are not so separate, not so independent. For example, this kind of robotics is a robot that is able to move on every land. This product is built by Boston Dynamics, that is a military corporation of U.S. Army. Is one of a class of one type of a class of robots that are able to run and walk in many different lanes. And the point is that it's a robotics that is connected to the sensory motor approach, but this is also inspired by something that is biological, like, for example, some animals with 4 legs, and is not so far from cybernetics. So we have a new cybernetics approach. The artificial part of human body for people that has no this part. So if you want to reproduce some robotical part, you have to also to consider how the mind, how the cognition, the cognitive part of an organism could behave with a new part of it and could interact with other human being or with the real world. Humanoid robotic interaction or human-humanoid interaction with virtual assistant. You have to, this is a very important field because you have to understand in which way a robot could behave in front of a human being, what is the reaction of a human being, what is the action that the human being could do in this situation, also the emotions, the feelings that people have. There is a very well-known problem that is called uncanny valley. That is the problem that regards the interaction, the feeling of anxiety that we have, that human beings have regarding some robots that are quite but not so similar to human beings. Other field are the connection between brains and machines for distance control, or the explanation of brains by brain simulation. There are at least 2 or 3 very huge projects all over the world that are for simulating a very big portion of brain. Human machine interaction. What are the best ways to use the cognitive capabilities and cognitive theories to produce intelligent program, especially in a linguistic interaction to improve the relation between human beings and computer. The support of artificial intelligence and cognitive science to the study of brain in order to understand the visual images that we can have from this with this kind of this is not just a picture of the brain. This is a dynamical picture of the brain, the functional magnetic resonance. So some techniques of artificial intelligence are used to analyze this kind of result, of experimental result. And finally, the question, the philosophical question on who I am, or who am I, or who are we, no? As a human being in this kind of world. And so that's it. That's it? No, it isn't. Because there are many other problems. New AI, new problems. I saw that new artificial intelligence is most deal with autonomous or bio-inspired or humanoid systems, because intelligence today is considered the capability to have an autonomous behavior in an environment, in an open-ended environment that is also a virtual environment on the net, but an environment in which we have to respond in real time. So this new AI, this new artificial intelligence, produce a contagion to philosophy, because create new problems, new philosophical, not only philosophical, but I will show you in the next slide some of them. Let's back to these two machines. What is the difference between these two machines? We saw that this is the linear idea of causality and the circular idea of causality that is typical of autonomous systems. But today we have other questions on machines. What is the difference between these two machines? First one, second one. Now, what is the difference? It's the technological enhancement, technological development. We have old and new 500. It's a very well-known car by FCA. But what is the difference between these ones? No? This is just a technological difference. Yes, it's a technological difference, but this is the Google car, no? It's an autonomous artificial intelligent system that replacing the driver. This is not just a technological advancement, technological development. It's also a different way of thinking, a behavior that is very typical in our life, driving. No? You have to change your mind if you stay in a car that someone else is driving, or better, no one else is driving. No? So, what is the difference between these three machines? This is a different way of considering the technological improvement of machines. So this is just one of main examples that I can do on these things. I have just another one. Other machines. What is the difference between these two machines? Sorry for the Italian of this. One, first machine, second one. Automatic gun, autonomous gun. No? This is the border between North Korea and South Korea. And this is an autonomous weapon. So there is no one behind this kind of weapon. And with this one, autonomous weapon with wheels, with track. It's very, very, very hard to accept a world with this kind of weapon. But they are autonomous system, and we have to, the problem is how to program this kind of machine if we have, because if someone can produce this one, someone will produce this kind of machine. Conclusion. Technical, engineering, psychological aspects gave birth to artificial intelligence and cognitive science. The evolution of artificial intelligence is related to the notion of intelligence and to new conception of mind and cognition. And so technical and engineering aspects are not so separated from this cognitive and intelligence aspect. New approaches and new problems to artificial intelligence and cognition are connected to these new autonomous systems, bio-inspired systems, maybe collective systems inspired by swarm, like ant colonies, bacterial colonies, who can say what is the future of this kind of machines. And robotic system, also swarm robotics, the idea that we have a collective behavior of thousands and thousands of same artificial autonomous system. So we have a lot of new philosophical, epistemological, ethical, political, legal issues and problems. But philosophy, the philosophy connected to this science, is always alive, and so this is the reason, because the philosophy of this science is also always alive and must be up to date everywhere, together with the logic required of it. So the logic is also the study of the linguistic ways in which we interact with the machine, in which a machine can, or an autonomous system can interact with us, and in which we can construct and use the knowledge that is structured in formation for program autonomous systems. Thank you.